so that we actually share a common advisor for the PhD. So we never met before, but so he's here to start collaborations with us, and it's nice to have you here. So.
Thank you so much, Danny, for that nice introduction and finding some time to. I know you had to spend some time to bring me here, or maybe and it's not very important now, but you spent some time to find my accommodation and all these things. So I will do my best to do some good work here. Okay, let's see. Yeah. So how to get my presentation? Yeah. So, share screen.
I think that you just need to push the door.
Okay. Is it seen? Next one. Yeah. Okay.
As is everyone seeing the PowerPoint?
Yeah. Everyone.
Yes.
Sharing the screen.
Okay.
Sí, se ve bien, se ve bien.
Okay. Okay, so I'll start. Okay. So I'll be presenting different problems which have been studying for last 15 years. Okay. Main focus will be on coupled flow and reactive transport. Then I also have some work on geomechanics, and I'll present some of those interesting results. So here is the outline. Okay, so I've divided into two groups. One is coupled flow and reactive transport in porous media. That includes the subtopics. And then coming to geomechanics and hydraulic fracturing. These are the few topics I have been working on it. I've got some interesting results I'd like to show you and want to get your feedback for next step in my research. All right, so let's start with the first one, the mineral dissolution precipitation promoting flow thermal instability. This particular one I did during my postdoc in University of Colorado Boulder. My advisor was Professor Rajaram, who was the PhD advisor of Danny also. Unfortunately, he's no more. Okay. And let's say there is a hot spring, and you know the hot spring water comes upward, and you may see like a pond like that. And this hot spring is located in a limestone aquifer, let's say. Then a lot of dissolution will happen. So let's say this is a conceptual model of the mountainous hydrology system. We have a strenuous slope, and there's a fracture, so the water discharge here and discharge here. If there's no evolution of permeability for all these things will be smooth, nice, but if there is evolution of permeability, things will be much more interesting. To do the modeling of dissolution precipitation kinetics and at the end the fracture or fracture aperture growth, we need to do a reactive transfer modeling. So there will be different way of doing it. So what we did, we considered 8 species originally dissolved, and one of them only in the solid, that is calcite in solid. And there are 5 equilibrium reactions and 1 kinetics. And if we use the component-based model, then we can reduce the number of equations for transport to 3 because there are 5 equilibrium equations. Okay, then further some conservations are there. Using them, we can reduce to 1 equation. So let's say we reduce finally to only 1 transport equation, that is a calcite, total calcite, total calcium. Okay, and we use Palmer et al. 1978 given formula to calculate the reaction rate in terms of concentration of different species. Okay, so this concentration, okay, these are the constants, they are function of temperature. So based on the concentration of different species, we can calculate the reaction rate. Another alternative, another reaction rate which comes from the mass diffusion limiter rate that is dominant when that is the that is to be used when the hydraulic depth, the aperture is larger. So basically you have to take a smaller one, okay? So to do that one, we have taken the harmonic average of the two, okay? So that we naturally will have, we do not need to any if-else kind of statement, we can naturally go to the which one is smallest, okay? Once we get this reaction rate, we can relate the porosity permeability change for rock as well as fracture. So for rock, it is this way. The porosity change will be reaction rate into surface area by molar density. In case of fracture, the dBdt, B being the aperture, the rate of change of aperture locally will depend on local reaction rate and so on. Once we get the aperture, we can find out the local permeability and so on. Apart from the reactive transport, we have to solve the flow equations that will consist of mass balance and momentum balance, Darcy law, heat transfer equations, along with the species transfers, which I said will be brought down to only one. So this is the general equation for three-dimensional porous medium. We have slight modification for a fracture. Okay, so in a fracture, one way of doing it, we can have the depth as an integrated equation for all of this, and consider the exchange of fluid, heat, as well as species. Alternative thing is consider the fracture also thin equivalent porous medium. So then you do not need to separately consider the exchange of fluid, species, and heat. It automatically takes care. Okay, so we used a software called ACHM, the finite element for heat and mass transfer, developed in Los Angeles National Laboratory. And it is a very robust one, but that software didn't have this particular transfer equation solution solver. At the same time, the porosity permeability alteration connection with the reaction rate. That was my contribution or my addition, contribution to the code. Once we did all these things and run the code for some years or 1,000 years or sometimes, okay, yes, we'll see evolution. So what happens here? This is the initial aperture field, which was assumed to be 0.5 millimeter thick, and the fluid was flowing upwards, streamlines rod vertical straight, so uniform flow, let's say. Now, with time, there will be more dissolution will happen on the upper part, and there will be Rayleigh-Bénard convection kind of thing will happen because of temperature is low at the top and temperature high at the bottom. The density is low. So the density is low here and high here. So naturally, it will not be stable system. So that stable system, that configuration will be unstable, will overcome the viscous resistance if the permeability is high enough. And this is only possible if you let the dissolution to happen. And okay. So what is the difference between general studies on Rayleigh-Bénard convection, whether it is porous media or some other fluid chamber? Here, the permeability is not uniform because the apertures are small at the bottom and large at the top. So the permeability field is something like that. And because of the advective convective heat transfer, the temperature gradient as well as the density gradient is also not uniform. So that gives some challenge to quantify the Rayleigh number, calculate the Rayleigh number. What we did, we calculated the Rayleigh number as a function of Z. So we calculate effective permeability for a certain depth. So I will explain that here. So effective Rayleigh number is calculated. Let's say this part has the higher permeability. So the thermal convection can happen here. Flow instability can happen on the upper part. So what is the average or effective permeability in this zone? We calculate based on this formula. And then we put them into this ratio. And finally, if we plot the Rayleigh number calculated based on this formula as a function of Z, we found it is a bow shape, it has a peak here, and So this is one set of analysis, and also numerically you can get the roll formation, that's instability also. We found the depth of the roll or height of the roll matching this height of the roll predicted by this calculation. Okay, and one more thing here. So there are in a fracture where the fluid is flow and reliable and convection, and this thing there are two types of instability. One is called instantaneous, another is called delayed. The instantaneous means if there is no heat exchange between the rock and the fracture, then there is a ratio already. I mean, in this paper or earlier paper, somebody stated that the appropriate Rayleigh number will be Rayleigh number calculated by this formula into B square by H. But the delayed instability, they said it will be proportional to B by H. So if we rescale the Rayleigh number and found it is based on this, when the instability happens, it is close to 60. So basically 4 pi square is like a 36 kind of thing, it is similar to that. Okay. And we did a lot of simulations for different initial aperture, different pressure difference, and found that the RA max after rescaling is between these two very small narrow range, 50 and 70. So this kind of analysis we did. Okay, and we published 2 papers out of this. One in Geophysical Research Letter, and another one is Water Resource Research in 2013. So for more, we can look into this. Okay, so now I have to go very fast. Okay, now coming to geothermal energy. So basically, whatever we have learned, the reactive transport module we have developed, applied to an engineered system. So here also a lot of temperature isolation thermal system, there's a lot of reaction can happen. Not only in a geothermal system, there is also thermomechanical deformation happen that I will explain in some time later. So you can see the different processes there are some process one-way coupling, some process both-way couple. Now, for geothermal system, we consider 2 types of mineral. One is silica-based sandstone, another is calcite. The purpose of doing it, okay, most of the things are in probably silica or amorphous silica quartz-based aquifer or reservoir, but calcite is also not uncommon. I mean, not uncommon. Okay, and people found there are some precipitation dissolution happens and well clogging. Say, concept. So here is interesting difference between silica and calcite. You know, silica solubility or saturation is increasing function of temperature, but calcite is decreasing function of temperature. One difference. Second difference is the order of magnitude reaction rate. Okay, please note it down that the temperature range I have taken different for 2 different things. Okay, so even at high temperature, very high temperature range, the reaction coefficient or rate is 3 order lesser than the calcite. So that makes a significant difference in the evolution of the aperture permeability or flow field rate. So if there is no alteration of the aperture permeability, then the flow field will be very nice. Some kind of doublet, not exactly doublet system, but anyway, source sink system. But if there is a precipitation or dissolution happens, so we are showing one case for each. So if we decide for this is the conditions, injection condition, etc., level condition, etc., we found there is a significant amount of precipitation happens, okay, which will come around the wells and that makes the flow field bit confined. Okay, so basically fluid is not allowed to go outside or not able to go out, overcoming the barrier, and naturally there is slight decrease in the energy production rate. On the other hand, if it's limestone, things are very fast. Okay, I mean this has been like 20, 30 years, 20 years, and this happens within within 1 year or so. Okay, slightly more than that. Things are very different. So a lot of precipitation and dissolution happens. So dissolution mainly happens in this zone. Precipitation happens outside, and the flow field is very, very confined. So no heat is coming from this part. So this cooling down is very fast. So heat temperature production rate is dropping very fast. Not a good idea. Okay. And one more interesting thing is that this blue lines is a contour. Basically, it divides the dissolution and precipitation zone that also evolves with time. So these things we found. I mean, I'm just showing you. Yeah. So things are very fast here, and of course very different from sandstone for two different reasons. I explained this. More. You are welcome to see these are our paper published. Okay, I will discuss all of it much more details if you want. Okay. Another interesting problem we solved much after that was basically CO2 sequestration, dissolution trapping in saline aquifer. So this is a typical reservoir they look for, where the cap rock. The formation will be this way, and CO2 will be injected somewhere in that aquifer with high permeability. And there's some geology, I don't remember all of it. But anyway, so what will happen? CO2, which is being injected in supercritical form, is lighter than the brine or water. But at the same time, it dissolves the water, and the mixture of that also being heavier than the water without CO2. So there are three different fluids of different density. Interesting buoyancy-driven convection can happen. Otherwise, there are also things which are important is the mobility or inverse of the viscosity. Inverse of the viscosity is plotted, is also function of temperature, heat capacity, etc., etc. Okay, some of these things may not be important right now, but anyway. So I said these are the three, because of density of three different densities, things can be very interesting. So I show some simulations results. So when CO2 is injected somewhere in the middle, somewhere in the reservoir, not exactly at the top, then it will go up, the plume, the supercritical free phase CO2 will go up, and at the same time, CO2 will also dissolve in the water or brine. We are considering, for numerical modeling, we consider the brine as a water, no other salt. Okay, it's an approximation. So it will go up, at the same time, this is the basically concentration distribution. Okay. And then what happens? These are the few things. So this is called the critical capillary transition zone, and this is this thin layer with a color variation called diffusion boundary layer, diffusive boundary layer, where concentration gradient is there. Naturally, density gradient is also there. At that part, small thin layer, becomes unstable, and the instability will evolve in the formation of thinness. Okay. Okay, so this is another one concern how fast the CO2 is moving. One another important thing to modular or practical application, you need to know how fast or what rate things are being dissolved. The dissolved CO2 is safe. If it is not dissolving, basically it will be sprayed, and if you find any leakage in the capillary, it will come to the groundwater and the atmosphere, which should be avoided. So what we found that when there is enough convection happens, sometime here at the onset of the instability of the formation of finger, dissolution rate increases. The point is, soluble fingering promotes for the higher dissolution. Dissolution trapping of CO2. That's what the subcount quantification here. Okay, so if we have so that's one simulation for isothermal system. If we have if we consider non-isothermal, which is the most of the cases, temperature is different from the reservoir temperature is different from ingestion temperature. So in that case, so if let's I have simulated two cases. One is 175-degree reservoir temperature, ingestion temperature probably, if I remember, is 25 degrees Celsius. So then, because of temperature difference, cause the density difference will cause one more big role like this, okay, which is similar to whatever I showed in my previous first set of simulations. So one interesting thing, here the rolls are big, height of the rolls are big, here the formation of fingers are very small. Then the reason is Rayleigh number is generally Rayleigh number being inversely proportional to the diffusivity. So you know the thermal diffusivity is order of 10⁻⁶. and the molecular density is order of 10 minus 9. So Rayleigh number coming from constant centigrade dependent density is 1,000 times more in case of soluble filtering. So happens very fast. Small h is sufficient. Okay. Now, one interesting thing we did, of course, I do not know whether it is how realistic situation, but if the reservoir temperature is beyond 220 degrees Celsius, because this is the point where the equation state, the data shows the brine with water with CO2 will be lighter than without CO2. So there is a intersection between the curves. Okay. So then, in that case, there will be no soluble fingers, but thermal convection will happen, and from the mound of the CO2 here, some fingers will be happen in opposite directions. I mean, I didn't bring the movies, but the movies are very interesting. I mean, of course, I could show it anytime later. So this is another set of simulations results, and for your kind information, we publish some of papers. Only 2 are being shown here. So this is for isothermal case. This is for non-isothermal case. If you are interested, you can look into it. You can meet me anytime. Okay, next couple of weeks. So I have a lot of long interest on flow instabilities. So when I studied multi-phase flow, all this thing, then I found, I mean, Professor Rajan, keep once like there's a fingers kind of things happens. He told me when I was in Boulder. Then coming to, after joining to IIT Madras, I studied this in some ways. So what happens, you know, when in a oil having a very high viscosity, can be 10 times to 50 times, 500 times, 1,000 times, depends on what kind of oil. To recover all water is being pushed, that's called water flooding, but sometimes they use chemical also like polymer surfactant for different purposes. The purpose of polymer is very simple, to increase the viscosity of the mixture so that the viscosity difference between the water with polymer and oil will be small to avoid viscous fingering. But polymer cannot be injected for a long time, it's expensive to stop. After it is stopped, there is one, so this is the water without polymer, water with polymer, oil. So there is 3 fluids with 3 different viscosities. Okay, and this is immiscible because this is water with polymer and this oil is immiscible fluid, but this is water, both one case has polymer and this is miscible fluid. So because of this, another interesting, we found that there are 2 immiscible viscous fingering happens, and actually there is 2 SOx forms, saturation SOx forms, each one become unstable. So this is the one of more interest, okay? And so basically, actually, there are 3 sets of fingers, form 2 immiscible, we are calling them leading, trailing, and then behind the polymer bank, this is called polymer bank, behind the polymer bank miscible. So what happens? Polymer also get absorbed into the reservoir. So, if you, interesting thing is here, if you inject low polymer concentration, then that will be lost in the reservoir after some time. So, it is not going to help. But if you increase the polymer concentration, let's say for 0.0 to 0.3 weight fraction, this becomes very stable, but this is the miscible finger, the finger behind is very strong now because the viscosity ratio is very large behind the polymer bank, and that those grow so fast they can penetrate the polymer bank and create a short circuit for water. So we published this paper in 2017 in Fuel Journal, and I would say this is the first time we have shown that combination of this thing happen. Okay, and recently after that a group of people from Purdue University published something in Porous media. Recently a JFM paper published almost similar. You can see that almost similar figure they have also shown. Okay. I'm not going to. So if you have 3, many wells like that, things will be much more interesting. Okay. I want to just discuss for a few minutes. Okay, this is also a reactive transport. Okay, this is also a reactive transport problem. Okay, reverse osmosis. Desalination is being done through reverse osmosis. That is, I think, most cost-effective process. So there are, this is the basic things, daytime filtration, okay, and the cross flow filtration. Basically, you can see the cross flow filtration, there is a fluid flowing over the membrane, and that helps to, reduces the accumulation of the salt particles over the membranes, and that accumulation of salt particles is known as a concentration polarization. So this is another schematic of that. And this is a concentration profile. So it's a reactive transport, of course. It's a reactive transport. I will show more reactive transport in the next slide. So this is a CFD simulation. A code we developed in kind of 2014, 15, I think, yeah. And main bulk of the fluid flow and transport of solvent access to it, but this boundary conditions and all these things we do separately using user-defined functions. So this is something we did later on. We further did this way. Considered a membrane scaling, the precipitation of calcium sulfate or gypsum. Okay, but what happens if there is a gypsum or calcium sulfate is also coming into the feed Autor module along with inertial like a seawater phase or other things? Then depending on the degree of saturation, there will be crystal forms. So as you know, all of you probably know more than me on that aspect, but anyway. So what happens? A crystal can form on the surface, that is called heterogeneous crystallization. If the crystal forms in the bulk, then it's called homogeneous crystallization. But homogeneous crystallization is, heterogeneous crystallization is more preferred, happens more likely to happen. Okay. So we modeled the formation of the precipitation and crystallization using a method called population balance based macroscopic method to determine the membrane surface coverage. So once the crystal form and they grow, the membrane surface will be covered, membrane permeability will be lost. So effective permeation from the Autor module will be reduced. So we could predict that. So phi is called membrane cover surface coverage, which is a function of M0 and M1. They are zeroth and first moment of crystal population. Okay, and these formula are available. Okay, but we put them together and modified the interface boundary conditions and the membrane. This additional terms comes because of the precipitation. It's like a sink term. Then permeability loss or resistance increase of the membrane is also incorporated, and we validated that model by other people. So the RAD get some kind of population balance, but not the same way. And this is an experimental result. I think I don't know, probably they did also. So the same. Okay, quite matching quite well. Okay. So we also not only stop there, we propose a different Autor modules, which is we call it a rotodynamic system, and we did all kind of simulations. We found, at the which the permeation will decrease because of precipitation. We found this kind of rotodynamic system performs better than conventional Autor module because of high shear, less precipitation, etc. Okay, so this thing can be shown in this paper. Now it's already 3:30. If you don't mind, I can continue. Shall I? Okay.
I think we can.
Another 25 to 10 minutes.
There's no time limit.
Okay, then I'll be going it slow if everything not necessary. It's so fast. Okay. Now my interest is to show what I'm doing it so that if you and others can also see the opportunities to come together. I like to visit this place. I think it's possible. Nice place. Very nice researcher. Okay. So geomechanics, I started from let's say 2013. Okay, sometime. And first thing I did with the EGS, then slowly moving to much more involved systems. I'll present some of them briefly. So when there's a fluid injection at high pressure, then reservoir cooling because of energy extraction, the thermoporosity deformation happens. Okay, so in a slightly simplified system, we model and see how things change. So what happens, given a certain boundary conditions and all this thing, okay, this is the temperature contours, okay, along this fracture. So you can see the cooling. Cooling means blue is the cooling, red is the high temperature. And because of this poroelastic effect, stresses are also being changed, and some places the effective stress decreases, some places effective stress increases. So it's kind of so basically this is injection well. So in between injection well, around injection well, aperture grows. Outside aperture drops. So like this is sometimes we will call it a kind of plate bending. Okay, so plate, if you press somewhere here, it will depress here, but some other place it will go up. So of course it's balancing all static equilibrium equation anyway. So if that happens, so this also actually confine the flow field. So if that is the case happen, I would say fluid will, I'm not showing the velocity vector plots here, but I am telling you that velocity vector plots will be only seen here. Outside this, there will be no flow. The vector length will be so small, it is no flow. So cooling will happen very faster, then the production temperature will drop also very faster. Other than that, what happens if you look at the ground displacement? So of course not much, 1 centimeter to 10 centimeter to 5 centimeter. So what happens at the very beginning, very early stage? I forgot to put the date. Maybe within a 1 year or so, the simulation has gone for 30 years. 1 year, or 1 month or 1 year, there is upliftment of the ground because of high injection pressure. So core pressure increases, causes the expansion of the rock. That's the reason things came up. And the cooling will cause the contraction of the rock, and that will cause the depression. So both upliftment and settlement can happen in different time, different time instances. Okay, so this was also shown in our paper. And I'll tell you one thing. This kind of observation already did by somebody else before us, published in 2017. But when you see there are 2 papers that we published showing some kind of things. But then what to do? Then we got some parameter study which I'm not presenting here. But then this was not being looked by anyone else. So we thought, okay, some new contribution we can bring it. And fortunately or eventually, this is the highest cited paper for me. I mean, I don't have much cited paper, but anyway, this is the highest cited paper. So probably many people are working on this problem. People like it for some reasons. We are also developing our own code in India, which will have. So far I used earlier codes. One is software from Los Alamos. Then another one is called UTCHM, very popular for oil recovery modeling, chemical oil recovery modeling. Okay. So what we are doing, we found that there is a need for it. I mean, when we started working on how hydrate sediment will, the hydrate bearing sediment will evolve with time. There's no particular code that includes all kind of physics. Okay,
Ours includes some of these things.
Yours is included.
Our code includes all.
Okay, we'll see that. Okay.
That's 30 years ago, so it's.
Okay, very nice. No, okay, good. So we did something. Maybe let's see whether we can. So we model the mass. Okay, I'll go into details then since you are here. So we calculate the mass balance using multi-phase flow problem. Then reaction kinetics, the dissociation kinetics. This is the one. We also included the elastoplasty. Is that?
And viscoelastoplasty.
Viscoelastoplasty.
In fact, the motivation for the code was viscoplasticity.
Okay. Good. I know because yeah. So then, of course, this is the energy balance equation. Yeah. So what we did, we did some results. Okay, anyway, but we validated the code with the Bell March by this. They published one paper in 2020. Which one is yours? Then is it because this is ours. The blue line is ours. all other from here. But is there any name?
No, as I said, that we are poor. We cannot participate in this.
Oh,
Takes
okay,
money.
that's okay. That's why
It's Coldbright. Coldbright is.
Code Pride, I know. Code Pride, I know.
I mentioned it.
Yeah,
Coldbright.
Coldbright is not there.
Coldbright.
Is it?
I mentioned it just now.
No, Code Pride, you mentioned to me that you are also part of the Code Pride. Yeah. But this is 2020. So when we sent a manuscript to journal, they said that please validate your code with the benchmark problem in this paper, and we did it. But a code pride was not there. Anyway, we'll see which one we have, which one we yeah, so things are quite different. You see, ours is one of them. Ours is one of them. I don't know which one is correct, which one is not. Ours is in between. I mean, nobody knows. Say, unless they do the experiment. Probably. Okay. Anyway.
But I don't agree with that. One thing is the reality you never know. But here, when you compare codes, you compute mathematical formulations, and the mathematical formulations you
Only
do.
one solution. Right?
So I don't agree with your statement.
No, but I don't know why the problem. But why so many different. Everybody is. There may be, of course, there may be some physics is different.
Actually, they are not so different. I don't see them that different. What is the bottom variable?
Which one?
The bottom one. The one that looks different is the one in the bottom.
Oh, the bottom is the
This
bottom. Displacement, vertical displacement.
This is radial, or which displacement?
Vertical displacement at the top, I think. Yeah, I think the displacement at this level. So the extraction happens here.
But the boundary conditions are very weird. This is very strange boundary conditions. Huh?
We have a doubt about it. I don't think if you tell me
Because
about it,
the problem is very poorly defined in the vertical direction, and therefore it's unstable. So I'm not surprised that you get a broad range. But that is not the problem of the codes. The problem statement is not good, I think.
Okay.
The boundary conditions.
Yeah, boundary conditions, I think is but
I mean, it is
we have-
unresolved.
yeah, we'll discuss it maybe later. What is the right way of taking? Because pressure boundary condition is not correct. Stress boundary condition. I mean, unless you take a very long domain, boundary condition effect will be significant in the.
Is that radial or
Radial.
radial? So in radial you're right. But the vertical, no. In the vertical direction, it is critical, the boundary condition. So I agree, in the radial, it doesn't matter.
Okay.
But in the vertical, no, it does not.
That's right. Okay, we'll see.
We have an analytical solution for this problem and
Okay.
illustrating this. By the way.
Okay, very good. Yes. We have just started it. So we could do two things. Publish two papers on it. And one is non-linear elastic, another is elastoplastic.
Our analytical solution is
I'll see that.
linear elastic.
That idea, of course, that is accepted. We'll see that, okay? We'll see whatever machine in our thing can. Anyway, these are things. Then, okay, another kind of, they call this fingers formation. They also call it viscous finger, but it is not the fluid, but let's say soft material, and soft material like a very loose soft material, and there is a injection of fluid in the center. Then, ideal case, I mean, in a stable system, the cavity will grow in a circular manner, but it doesn't do that. Okay, so this is an experimental. People have done this experiment earlier, but nobody did the theoretical modeling of that, and we have not done that. We are going to do that sooner. Okay, so far we have done this axisymmetric problem, assuming the cavity is circular. So what we did, there are three different zones. When the fluid is injected, the fluid is permeating, so waiting for propagation. At the same time, the vicinity of the cavity is a plastic, outside is still elastic. So there are many interfaces. One interface is, let's say here, one interface is dry and wet. Another interface is elastic and plastic. So we are going to track three things, A, C, and S. So it's been done mostly analytical or little semi-analytical, considering assumptions, many assumptions, like no porosity parameter change, no associated fluid. Most important assumption is more Coulomb criteria. Any other complex plasticity model will not let us do any analytical modeling. It's only possible using like a bilinear, more Coulomb criteria and these things. And this is something we predict. So this is zeta is we call that the permeation coefficient that starts slightly smaller than 1, then grows, and how the cavity growth, the permeation front growth, elastoplastic interface growth is managing. But now we are what we are doing, we are considering porosity probability change. We are not using more Coulomb, but we take Camp-Clay model. Camp-Clay model, doing a Camp-Clay model, we are using finite difference method to solve the problem. I mean, it's a grid-based problem, like not anymore analytical. Okay. We are working on it, done, will be done by end of this year. Okay. And something also we did some hydraulic fracturing. So what I will say, when the hydraulic, when the fluid is injected at different wells to create the fractures, of course, this is simplified. But even though it's simplified, I would say not many people consider many natural fractures and an interaction case we consider, and that we found how the fractures get connected. As the fractures get connected, we can have a higher probability. Of course, we would like to have not short circuiting, we would like to have more fractures far away look at gets connected. Maybe that has to be understood by doing many more simulation. What is the technique for that? But at this moment, this is what we could do. And what is the objective of doing this hydraulic fracturing is essentially increase the permeability field or translucidity. So that has not been done anywhere. I think 5 years ago, they proposed one method to get the permeability from the displacement field and the damage field, but I think no. I was able to formulate it, but other things forgot the old paper. But anyway, they did it. But we put them all this thing in our code and calculated the permeability. And there's two methods. I don't know the details. So if that's not connected well, then the discharge between these two wells, when they are not connected, is less order of less order like 0.004 kind of meters per second. When they connected, then we can get measuration. One method we can get this number, another method we can get this number. So it all depends on what is the reservoir permeability. This number can be also 1 or 2 order difference. It's like a old slide. So I'm not going to do there. So basically, permeability calculation is something which you incorporate in your model. I'm sure. Yeah. So I think this much. I should have one more, but I don't want to do it right now. Thank you for it.
But can I start?
Yeah. If you know that.
This is one question on the heat injection with mechanical things. You also know.
Methane?
In slide 27.
27. Okay.
I think you have your heat injection 27.
This one?
Yeah. I have if you inject heat.
No. We don't inject heat, but we inject cold water and extract. This is geothermal.
But there is heat.
There is a heat extraction. Not heat injection. Heat extraction. The cold water is going. Geothermal application. But
because you mentioned it's coupling, etc. So I was wondering, does this model also include reactive?
No. This is hydromechanical. No chemistry.
Another model is also.
Yeah, it will be what we will
But it is very similar to the one you had with the silica and the carbonate.
Yeah.
Yes.
I think it's basically the same. So in terms of
Yes.
But no, because I was wondering, is it important to because there could have been porosity change or something.
Yeah,
Would that also affect mechanical things?
it is important. If we really, if it's a real reservoir, they are supposed to predict its lifetime production rate. We must do all couple system. It's but we have not done that. We have stopped here. And what happens sometimes in a place that one student finished a PhD, that problem stops. New students comes, is a different interest. Now I'm doing something different. That's why, sir, I have to change my area several times, which we have been noted. Okay, it is a case for. Yeah.
So,
Yeah.
Abhijit, so thank you for the slides, and it's clear you've been working in a lot of different topics throughout the years. Always in the side of thermal, hydro-mechanical comments, very interesting. I'm wondering, especially about these figures you
Yes.
showed at some moment,
Yeah.
because how can you discern or differentiate whether these patterns are somehow a numerical instability rather than a physical instability? Is there any criteria here you use for differentiate this instability?
So one way of doing it that we can do the grid sensitivity, and if we see that they are not changing with the different grids, then we can think of still physical. Okay. I think so.
So that there is a sort of convergence analysis involved before these numerical models.
I mean, we didn't do anything very rigorous way, but we do what we call grid sensitivity analysis, and then we ended up, yeah, this is physical, this is no more changing. Of course, I mean, if we have a very coarse grid, fine fingers will not be shown. But anyway, fingers are quite thick enough than the individual grids. But that is something. Anyway, numerical perturbation, which also helps to get the instabilities. So we need some kind of error in the numerical solutions. It's not there, then we won't get. Yeah. But we don't add any external perturbation, no heterogeneity there. So it evolves. So basically, the error itself.
Is there a reason for that? I was also wondering about why you have avoided heterogeneity sometimes.
Heterogeneity?
Yeah.
No, well, okay, of course, reality is heterogeneous, of course. Yeah, I mean, we have to do some studies, right? We have to go step by step. Maybe the next step will be doing more. If you have a real data, it will be much more interesting. It is all like things that most of my work is like a hypothetical, I mean, not hypo, I mean, some kind of simplified synthetic reservoir, simplified system. The problem in our country, there is not much of interaction between the industry. We have some industry, government funded, the public sector, but they don't share with us much. So that's the problem. So we have to do all like theoretical studies like this.
If you allow me to add for Rodrigo's sake, this, because it illustrates many things about physics and life. The initial perturbation is almost random, and in his case, is purely numerical. And in fact, you can see, actually, you can see that this is a good model.
Okay.
Because when you look here, you see this very small wavelength.
Yeah.
The very small wavelength, numerical, 100% numerical.
Okay.
You change the grid a little bit,
This will change.
and it will change.
Yes, absolutely. Yes.
And the one that starts is like the one of you, some of you, one of you here will get a big assistantship, a big project. And then your life is solved. You will be getting projects all your life. If you get an ERC, your life is solved. This guy here started, he will succeed. It will be because it's a capitalistic system. This one will draw the fluid from the other ones, and this is the one that succeeds. So while this is random and this wavelength is very sensitive to the grid, this is not.
Okay.
So, I mean, the exact geometry is somewhat random, but the wavelengths and these type of things are not. And I don't know in this particular example, but in general, they are realistic. And you can solve it mathematically.
Yeah.
And when you get numerically, in general, it's
Yeah.
consistent with the mathematics.
Yeah, I think Yeah,
the
so-
same,
Huh?
the statistics.
But they don't, I mean, there are two critical points here. One is the onset time,
Yes.
when does the instability
Yes.
start to grow,
Yeah.
and the other one is the wavelength of instability.
Yes, the other two. So it's possible to do radically by kind of normal mode method or so.
Yes.
Yes. So people do normal mode method. And, this is a bit complicated for radical because but anyway, slightly simplified.
Oh, you linearize, of course. I mean, yeah, sometimes it is complicated. I mean, this
Yeah.
is viscous instability.
Yeah, so, but
Caused by viscosity.
lot of
You linearize that.
lot paper from 1980s published on the miscible, immiscible fingering with analytically. They not did normal mode method, then got a best state, the normal mode method, all this thing. They got a wave spectrum where which wave number will be dominating. If that matches with our numerical, then we can see numerical. That's kind of yes.
Because this is because it's homogeneous.
Yeah. Medium is
In my opinion, the numerical error that you need to create this perturbation is needed only when it's homogeneous.
Yes, yes,
When
yes.
it's heterogeneous, it
Oh,
doesn't matter.
No. You don't need no. Even if you make a perfect square grid, yes, the numerical, the round of error will create this.
Oh, yeah, but
So when you do not need to do anything, it just happens.
But when it's heterogeneous, the start and everything, it's ruled by the heterogeneity. It's not ruled by the perturbation, the numerical perturbation.
No, no, and sometimes even all the way to the end. I mean, if you have a very high permeability, the low viscosity fluid goes to that, and that's it. So I mean, instability requires some sort of homogeneity. At some scale, you need some homogeneity. But if you have a high permeability fracture in the middle, all the low viscosity fluid will go through that. That's it. I mean, it's not so. Yeah, we are more of a heterogeneity types.
Yeah.
But sometimes, for instance, for unsaturated flow, it's this instability. In that case, it's gravity, density.
Yeah, I know.
It's it overcomes it.
But this is something inherent to finite elements? Or
No,
this
this is
is
physical. No.
This is physical.
differences? So I mean this random instability generation because of the random error.
No, round-off error is a machine. It's a machine number.
Yeah, but if I have a regular grid,
Still.
You will always have round-off. You always have. I mean, you have
but it's
80.
if it is homogeneous.
Round-off is the machine.
Yeah.
The machine capability.
The epsilon.
After the 16 digit is random,
Yes.
this is sufficient to generate.
Yes. So it is nothing to do with the numerical methods. Any method will give you the same. Yes. Not even have difference. Yeah. So just quick thing, I just wanted to tell you because I just.
But this I don't know, Jesus, because at least with UFA, if you make it homogeneous and you don't add artificially a perturbation, you will not get fingers. You will get
Actually, this is no. Actually, this simulation homogeneous medium, no artificial perturbation added, but numerical errors actually work as a perturbation.
But I don't know if it's
Okay, so
numerical
one thing is
complication
that,
or I don't know if it's numerical.
Have you ever tried to solve explicit in time the simplest diffusion equation explicit in time for a delta G greater than the critical delta T?
Yeah.
Everything homogeneous, everything perfect, you always get
Yes.
this infinite oscillation. I mean, physical instability is there, it's real.
But that's numerical complication. That's not runoff.
And that's true. But in
That's
the
what I
end,
think. That in my opinion, I don't know whether it's runoff or numerical complication, but
Exactly. But these are all
it's more like
implicit.
numerical
no, the
complication.
problem is that it is unstable. Whether it is called by Randolph or by numerical, in the example I was telling you is numerical. But the point is that if it is unstable, it will occur.
Oh yeah.
Yes.
So I did one experiment or experience long time before in Boulder. I'll tell you when I was doing oil conversion, I was adding temperature perturbation in like a certain intervals. That was told by Los Alamos, the George Jablonski. So he told that, and I was getting the results, and without that also I getting the similar results, almost same I could say. So that extra additional perturbation was not needed. Numerical error was sufficient to trigger the onset. Okay. If the idealistic system happens in reality, probably will get the same onset time, same growth rate. That's what we are doing.
No, actually, there is a time you may reduce a little bit.
Yes.
A little bit by
Yeah, of course, yes. So that is the, maybe slight, but not way different, not order of magnitude different. Acceptable. I mean, this is, once I got that experience, I think let's not, because putting the temperature perturbation 1 or 2 days, couple of simulation time step is tedious. I mean, I had to do it manually, I had to write a code, so I stopped that. It was working.
At the beginning, you showed that was very nice. That picture with the springs, that was very nice. So why in your simulations you have 2 springs? Why not 3?
Okay. That depends on dimension. It depends on the that actually I'll tell you the relevant convection in a certain size road, it's like a circular, and I have taken dimensions like a 1 kilometer or 2 kilometer, but 3 kilometer probably I got 3 third one. It is generally circular. So it depends on again, the high rally number, it will be very narrow like a what do you call it?
So for each circulation you have one
line. Yeah.
You have 1 spring.
Yes. So it depends on. I mean, I will tell you if it was. So what I didn't tell you that time. There are in this context there are 2 kind of things we call. Because instantaneous instability, another called delayed instability. So if the diffusion happens, the temperature diffusion, then delayed instability. Then the Rayleigh number requires, one is absolute Rayleigh number will be much smaller. Other one, it will be, if you don't allow the temperature to dissipate or temperature to exchange between this, then called instantaneous. Then immediately it will happen, but it requires very high Rayleigh number. In save some time, I'll come to your place. So in that case, the high Rayleigh number situation, roads will be very narrow. And if that is the case, then you may get many things. But anyway, it is nothing, it's something, it is beyond our, it happens and happens. But for this kind of, since you have taken 2 meters, so 1:2, and in circle, 2 circle you can fit, kind of, I can think of.
No, that's very nice.
Yes.
It looks so much to your first figure, huh?
Yeah. Okay, so good thing I just want to tell you, if you know anybody working on this, I can meet them because this is something I'm doing right now. So we are right now working on this problem. This is very interesting. We are developing a system. Not alone. There are a group of people in Spain probably also. So we are developing a system which will take the wave energy from the waves, and pressurize the water. Then do the desalination the arm. Okay, so the energy will come from the abundant waves, will give the energy. No electric energy from the grid. Okay, no electric energy from the grid. And the water will come from the sea, but the output will be potable water, drinking water or fresh water. So,
How do you do that?
how do we do that? We have wave energy converter. Yeah.
No, I was just making that question. Well, I understand that you can maybe use the energy of waves to desalinize.
Yes. So,
the process.
yeah, the process I will show you this slide. This is a slide. This is a flow chart, how things in the water will come here. And this is one of this. There are different types of wave energy converter. One is called clap, and it's called surge converter. So as the wave goes, it goes up sidewise, in relation of wave, and it pumps the water. And if it comes to the pressure accumulator, the pressure will increase. So let's say this is connected to the this is the hydraulic cylinder which is connected to this kind of flap, And then as the flap goes because of the weight, the water will water will enter in the system, the high pressure will increase in the side. Then when the pressure is sufficiently high for desalination, okay, overcoming osmotic pressure 50-70 bar, and will pass through the RO. So this is interesting. We have been doing it. We got a project in India also. Okay. And in fact, there's a DOE in US, they make an announcement for a competition. Many European, American, always it has to be one partnership in US. So we got a University of Hawaii. They went there. So there are 5 stages. We own up to 2 stages. Okay. But still we are working on it. So we have 2 models. One as a converter. One is this one, another is called point absorber, where a buoy will go up and down as the wave passes, and accordingly it will pressurize the water. So
but then you need some filter. You filter.
Yeah, filter will be needed. So there will be a lot of filters.
So you just reverse osmosis.
Reverse osmosis.
But the pressure is done by the.
Exactly. But reverse osmosis is the last stage of the filtration. We have to filter using activated carbon filter, sand filter, activated all these things. So one after one, different size of particle will be eliminated. Then this is the layout of the things. We are working on it. We'll probably in 2 years' time we'll develop a physical system. Okay, we got the money from India. Government gave us something. But we have to know that if anyone in EPC works on this.
So you want to make a desalination plant inside the ocean?
Yes. Yes. So, I think Spain there are many other universities working, but I cannot. But if there's anybody in this university, we can also meet them. See, my purpose is to collaborate with you people and come here often. If I come for one reason, I can do the other one also. Right? I come for, then I can work with you. This is the thing I am doing it nowadays. I come with the multiple. Someone has to call me. Very nice place. A very nice place. Very nice. Best.
Very nice.
Okay, please let me know. Anybody? No?
There are no other questions. We leave it to this. Thank you.
Okay. Maybe we should basic Jesus.
So see, I think he wanted to talk a little bit more, and we had another meeting. He has another meeting in the bar.
In the bar.
So is it?
Okay. Okay.